All right, everybody, welcome back to another episode with Sharp Education. I'm excited for this episode. This is going to be um, a lot of movement in the right direction. You guys might have noticed by now, but what I'm trying to do is set us up for training and test splits. So, what that is where you have all of the data that we're working with right now in two different parts. Right now, what we're doing is we're fitting our models to all available data. And what that creates is something that's known as overfitting. Overfitting is when a pattern can be identified in a data set that doesn't suddenly apply to future data. So there are patterns that always exist in a data set. No matter what pattern, no matter what data you're working with, the machine can identify patterns there. But whether or not it can extend those patterns further into real useful information in the future is the entire difficulty of machine learning. This is known as overfitting, and you need to minimize that in order to gain what is known as generalization or an effective understanding of where patterns will continue existing in the future. I don't want to just ramble on and on and on because we're not quite there yet. Today, what I want to do with our logistic regression model, yes, even though we have both logistic and linear regression models, I'm going to be working with logistic regression today to try and optimize it and understand exactly what I want to work with before we get into training and test data. So here's how I'm going to do that. First, let's load in the data, same data that we got from our other logistic regression model. So we have everything including the MACD histogram. I'm just going to take the global variables, Control C, and I am not going to paste in the strategy just yet. Get data. It's also going to be here. So now we're just going to be getting the same data. Define main df equals get data and return data frame. That's our main function. So when we do data frame equals main, we look at the data frame. We have that close price printed out. I'm going to get rid of that. And this is what we're looking at. Open, high, low, close, and volume. So you might have noticed we're working with absolute values. And I'm going to turn auto adjust back to true so we don't have these separate columns. Auto adjust true. So we just always have these close prices as adjusted close. Now, working with absolute prices isn't super useful. I couldn't imagine seeing one day, okay, share prices today are $436. Now, 436 is statistically significant because 312, 20 years in the past said this. It's not very useful. So what we need to do is something known as, well, something I'm going to be referring to as standardization. Standardization is a complex statistics term used to define taking everything benchmarked to its z-score or how far away it is from the mean based on its standard deviation. We're not doing that. We are instead just going to take all of these open, high, low, close, and volume changes. So what they did relative to what they were yesterday. So now we're going to have columns that show their movements on a daily basis as opposed to their absolute values every day for 8,168 rows. Because this right now, in my opinion, is useless information. There's no one number that's more reflective of a movement than another absolute number. But a percent change, if it's a greater percent change as opposed to a smaller one, then that could mean a more significant future movement in theory, just if we're building a narrative. And that's what a lot of trading influencers do. And anyway, so let's take a look at data frame columns. We should have a list here, columns. Right, so we do have a list. Now, what I want to do is get the percent change of close, high, low, open, volume. So what if I, instead of keeping it like this, I set data frame for C in columns. I want to loop through each of the columns. So data frame.columns, which is, as we now know, is a list. Let's make a new column with that change. So data frame, and it's going to be an F string. So C change. Whoops. is going to equal data frame and then another f string with the name of our column, which is c dot percent change. And this is a function built into pandas. So what this should do is, once we have our data loaded in, it should give us extra columns with the percent change each day. Now let's just run all of this. And I'm also going to get rid of the plot because I think that's unimportant at this moment. We know what we're looking at. If we just take our, now you can actually see we have these extra columns, close change, high change, low change, but let's just do this. Perfect. So the percent change was 0.07%. I'm going to multiply these by 100 because I feel like 0.7% is more effectively demonstrated when you're doing it in terms of 100 as opposed to in terms of 1. I don't like looking at percentage terms in terms of 1. So we have 0.7% change of close prices. So now close price increased by 0.7%, increased by 0.2%, increased by 1%, so on and so forth. So this is good information. Now, instead of looking at absolute numbers, we're looking to see how these percent changes are impacting whatever our target variable ends up being. So let's move on with our data acquisition now that we have this as our data frame. Wow, there are some really drastic changes in volume at the beginning of the S&P 500. Okay, so I'm going to give those back. So now we're working always with relative movements, which is more useful. Great. So let's move on with our study. For our study, I only want to use Bollinger Bands as an additional technical indicator. But before we do that, I actually just want to set up the study to handle no technical indicators, just the price movements, to see if that gives us more information than what we were looking at earlier, which was price movements and a technical indicator, or just absolute prices and a technical indicator. So now we need to add the target variable. Let's go to our add target variable. Here it is. Control C, Control V. And our target variable is a binary 1 or 0, depending on whether or not prices are greater than or less than they are at any given row. So when we have shift equaling 1, our binary is just whether or not tomorrow or the next hour or the next minute is greater than or less than the current price. So if we shifted this to 1 hour, it would be 1 hour from now. After we have our target variable generated, we need to then generate the regression output. So we go back to Logistic Regression, to IPYMB, Control C, Control V. Perfect. In our strategy is now going to be the list of columns. So let's get dataframe.columns. And I want to paste this in, Control C, strategy equals this. Great. So now we have a column. Remember from our logistic regression that we define strategy as the number of, or whichever columns we are interested in regressing on for our target variable. So now we're doing high change, low change, volume change, so on and so forth, as opposed to their absolute values. From there, I want to take a look at the confusion matrix, an ROC plot, and prediction distribution, all of those beautiful charts. So let's paste those in as well. So let's add the confusion matrix and the ROC plot here. C. And the prediction distribution, I'm going to make a separate function for it. We have it right now in generate regression output, but I actually want it to be here. So define plot prediction distribution. Perfect. And what we need as arguments are y pred probability. That's it. So we got y pred probability. Cool. So that should be it for now. If we add all of this to a main function, data frame now equals add target, generate regression output, and add confusion matrix. Okay. Okay, so now we have all of our functions with all of their arguments that we spit out from our generate regression output. So we're adding the ROC plot with the area under the curve, and we have the distribution of predictions and the confusion matrix. Perfect. So now what we have is still that pretty weak ROC curve and the area under the curve score of 0.52. We're working with daily data, and on the S&P 500, when we're only looking at percent changes of the open, high, low, close, and volume, the performance of this chart, of this model, is not very exciting. Now, let's compare this to our outputs that we got when we were using absolute values. I'm going to be doing a side-by-side comparison of what it was looking like when we used the absolute values versus the percentage changes of the open, high, low, and close prices. So let's take a look at the p-values of each indicator. So we can start with the close prices, which were statistically significant when everything else was held constant when we're using absolute prices, 0.014. And the close changes are even more statistically significant, but that's the difference there isn't enough to change your world. So let's look at the low prices had 0.018 and the low had 0.17. So that's worse. High change went down a little bit. Open versus open change went significantly down. It's 0.02 as compared to 0.3. So to me, it looks like on average, our statistical significance for the change in prices is more important or more impactful than the absolute values.